Okay, we're ready to start. Welcome. This session is titled "A Million Agents is All You Need." And it's not just clickbait. I'm actually going to talk about that and try to make that argument for real, scientifically. I'm Risto Miikkulainen. I'm VP of AI Research at Cognizant AI Lab, which is just a couple of blocks that way on mission. We have about 35 people there, and I lead the research part of it. But I'm also a professor at University of Texas at Austin, computer science, hence my cow here. And that's very interesting how industry and academia have come together this way, that they actually need each other, and it is possible to have one foot in both sides. So, Cognizant AI Lab is part of Cognizant, which is a very big company, but we are kind of a special unit right under the CEO, because we are doing fundamental research in AI and spearheading the efforts of Cognizant to lead in AI. Like I said, we're pretty small, 35 researchers. Most of them are in the picture. And what do we do? Well, we mostly play ping pong, and sometimes between sets we also do some research. This is actually from our office, and you can recognize there's a Salesforce Park right in front of it. So it's a gorgeous place to be working. We do fundamental research on problem solving, generative AI and machine learning, evolution optimization. So multiple different technologies come together to do something like this, decision AI. And we also have AI for good use cases, so land use change, rehabilitation after a stroke, many projects like that. And also, of course, there's business outreach as well. So other people in Cognizant take the technology, then build platforms, and take them to the clients. And that's what brought me to Cognizant and industry. That I was in academia, and I'm still in academia, and I've been for 30 years, and a lot of times you just write papers to impress your friends. I wanted to do something that actually might have an impact, and that's what we are doing. But we start from grassroots. We start from the hardest problems, and then they address issues in the world, and then we'll try to make a change through that. So this is one big project that we just finished. As a matter of fact, we announced this book yesterday here, today in Japan, with a couple of colleagues from Sakana. It's about neuroevolution, using evolutionary optimization to construct neural networks for all kinds of tasks, mostly for behavior and decision making, but also for generative AI, optimizing large language models. And they also give insight to biology, learning and evolution. So I can shamelessly plug it because I'm not making a penny of it. We gave up all our royalties so it can be open access. So anybody in the world can click on that button and read the book. And take advantage of all the other resources like tutorials and demos and exercises and so on. So this is actually a lot of what I'm talking about today, but this puts together a whole historical perspective and comprehensive perspective on that area of research. Okay. Yeah. So what we see as a change that's pretty much happening already is from AI models to AI agents. This is not news. I mean, everybody talks about agents. It's just that we've been talking about agents for decades. All of that book is about building agents. So instead of predicting what will happen using a big data set that you might have from your business or healthcare or education, wherever it is, we are building AI systems that make decisions. They do things. They actually interact with the world, not just predict what will happen in the world. So it's a very simple perspective, but it's very powerful. And it's kind of scary, too, because you have to give agents some power in order to modify the world, and hopefully you can trust them. Now, so agentic AI, it's been about a year that we've been talking about it, but one extension that we really like to propose for the future is multi-agent AI. So it's not just that agents are impacting the world. They're actually talking to each other, and they are negotiating. We all have agents that represent us, and then they talk to each other and come up with better solutions than we might with a single agent, perhaps. So it is kind of pushing the agentic AI to a next higher level. And this is not yet happening. We have some tools, and we have some examples of that, but deploying it is what will probably happen in the next year, couple of years. So multi-agent systems have been around forever, decades. But what's different now is that because of LLMs, they can communicate with natural language. So we don't have to build complex protocols and design these interactions like it used to be in a couple of decades ago when multi-agent systems came out. But they can actually be really naturally discussing problems and negotiating and coming up with answers. And we can see what they are doing. So that's why multi-agent systems are a really compelling direction for the next couple of years. So one thing that we built in the lab, in the Cognizant AI lab, is a system called 𝗦𝗲𝗀, a platform called 𝗦𝗲𝗀. And it is intended to be an orchestration mechanism for multiple agents. So each of these little circles is an LLM. Well, it could be something else too. It could be a machine learning system that makes decisions. But in a demo, they are LLMs. And we have specialized them using these system prompts, like you see one here, the payroll agent. These are instructions that you give. What is your role? What do you do? What do you know? And this is similar. It could be a job description for a human or something like that in an organization. So it comes very naturally. These kind of expertise definitions come very naturally. But then they have access to other things. They have access to documentation using RAG, and also current data from the company or whatever the domain is. It might be coming in real time. And they have a library of tools that they can use. Web search tools, calculations, things like that, simulations. So they're actually quite powerful in a modern way. They're not just LLMs that try to shoot from the hip, but they have access to resources. And each one knows what they are doing. Okay. So this is how it works. First, you have to build that. You have to define all your agents. And then you have one agent that's designated as the front agent. And that's who you talk to. You give your question to the front agent, who then assigns subtasks to the other agents. And these interactions are defined in a protocol. We use something from a couple of decades ago called AOSA, which really works actually quite well. It was designed for another era, but it has to be adapted to the current era. But it does work quite well. It establishes what each responsibility is, how you resolve conflicts, and how you combine answers. So it gives you that ability. And each agent then gives you an expert perspective. Like the question was, I'm getting married, what do I need to do? So here are some answers from IT department and from the finance department, and there's benefits, and there's legal, and so on. So I'm going to show you actually a very quick demo of how this particular use case works. And this is now live on the internet. I just have to pull it up here. Okay, where's my pointer? There it is. Okay, so this is actually a live interface to 𝗦𝗲𝗀, and this is a network that was designed to do that. It's a company intranet. So it has all these experts on payroll and finance and legal and HR and IT and so on. And they have sub-agents that specialize in different aspects of those functions. And now I can go here and ask a question. And the question might be, indeed, I'm getting married. I maybe just point out that I understand there are many updates I have to make in the company intranet. Please check, I don't know, what they are. And don't leave anything out. Okay, so now this goes to the front agent that's highlighted. It's now thinking, it's accessing its resources, and it's sending something to HR, a question, okay, here's what I want to know. And now it goes to other aspects of the network. There was a question to payroll, and now back to HR. So this is the part of negotiation that happened. I never meant the procurement, legal now, and I think at some point we'll drop down to immigration to ask something. IT was there. So this is not just static retrieval of information. It's actually dynamically collecting this and then negotiating and saying, okay, here's an interesting perspective. Can you add to that? Is that going to cause a conflict? So in that dynamic way, we then collect all this information and we get an answer. Mostly it's about benefits. You have to think about health insurance and retirement plans and payroll needs, marriage certificate, there's legal compliance. Sometimes we get more like about immigration and so, depending on what your background is. But this is basically the idea that it's not just information retrieval, but there's an active processing of that information, negotiations and conflict resolution. And hopefully you don't miss things that you might if you go there yourself. And this is actually a system that we are using. I mean, it is deployed in Cognizant in India. There are thousands of people who use it. Currently, it's limited to travel planning, but we will planning on expanding it and making it available. And we're learning a lot about load balancing and what kind of unreliable answers, what to do about those. But by and large, it's working. And I think this is the way of the future. If you have an organization, you of course have people still there, but you also have this AI network that will help those people to make better decisions. They have access to information, they know how to process it, and give you more than you could just by retrieval of documents. So here are some advantages. Divide and conquer. So you're making a big challenge much more manageable by breaking it into smaller chunks. And that I'm going to talk about in the end, a little bit more. But also just multiple perspectives. So if you're trying to reason about something, you don't get stuck because you can always bring in a new perspective, a new agent that might get you unstuck. But there are also practical advantages. You can have general agents that give you overall answers and specific agents that may handle special cases. Also open and proprietary agents. So your company agents can be proprietary and talk to some other agents that are public. And you can also improve these agents incrementally. You can change one agent without disrupting the rest of the network. There's also a lot of opportunity to making these systems safe. Because it's modular and distributed, there's redundant processing, and you may catch errors because there are indeed multiple perspectives. And you can have agents whose job is just to find these errors and correct them. And you can have humans in the loop too. I mean, one of these circles could be a human. You ask Joe, when you don't know. And that is perfectly possible as well. So this software is actually available, open source. If you go to that website, if you just remember cognizantarlab.com, you'll find everything under there. But this is a GitHub repo, and you can implement your own networks very easily using this open source software. All right, but I'd like to talk about a couple of other things that are coming up. This is already, like I said, deployed, but we're still building a lot of these networks for clients, and anybody can download the open source and try working on it. But there are new technologies as well, and here's three. One of them is trustworthiness. We still need to understand how well we can trust these LLMs. And fine-tuning, like in this multi-agent network, sometimes it's okay. You have a different document that you can lean back on, but there are also skills. There might be math skills, reasoning skills, negotiation skills. So you might want to fine-tune your LLM to be a skillful expert, not just an expert that knows where to get the information. And the reasoning is also a challenge. And by reasoning, I don't mean just a couple of steps, logical puzzles, but reasoning that happens in the real world that may require a lot of work, many hundreds of steps or thousands of steps, millions of steps, actually. So we'll look at those in the next few minutes here. OK. All right, so first one was the trustworthiness. So it's still the case that LLM agents make up answers without warning you. And you don't know. They don't tell you that, I'm not really sure about this, but I guess. They don't really do that. They just give you an answer, and if it's correct, great. If not, you have no way of knowing. So, and that hasn't changed, even if we now rely on a lot of sources in the internet. So it would be really good to have an estimate, a numerical, perhaps, evaluation of how trustworthy a particular answer is. I mean, sometimes this information is still useful. An LLM makes a guess. Well, it is an educated guess, and you could take that for what it's worth. If you know that this is trustworthy at some lower level, you can still take that into account in reasoning. So that's what we're trying to do. So here's an idea. We have a query, and we ask the LLM to produce multiple answers. And you can just sample an LLM multiple times, and you get different answers each time. I'm sure you noticed that. You ask the same question, you get a different answer. And you can adjust the temperature to make it more consistent. But that's really in the nature of LLM. I mean, it is generating many plausible alternatives by its very nature. So we could use that ability to estimate how reliable those answers are. And it's a very simple idea. You measure distances in semantic space. So here's one answer, and here's another one. They are actually labeled there. And you can even draw this little visualization where the most dense area is the bright yellow. And answers that are closest to that dense area, they are more reliable than answers that are somewhere in the boonies there. That's a hunch that might work. But it turned out it actually is working. It's a good principle that if LLMs generate answers, certain kinds of answers a lot, they may be more reliable. So, so this is some data on what we did. Notice this has to be open source models because we have to go there and sample at will. So we have to be able to access some of this. And this is an important point. Open source LLMs are absolutely critical for doing research because we don't necessarily retrain them from scratch. We can't pre-train them. That's too expensive. But if they are open source, we can do a lot of other kind of research on them. And this is indeed what was done here. Llamas, Mistral models. We used 𝗀𝗀, we used DeepSeek and other models that are open source. And here, this little table just shows you that when you're using semantic density as a metric, it will give you more accurate estimates of reliability than some of the others, like semantic entropy and actual probability that you get from the LLM itself. Let's look at this now in an interactive demo. And here it is, again, my little interface here. Let's go to a different one. This is now the demo of semantic density. And we can ask a question. So this goes to, I think this was a llama model. So let's see. Something where there isn't really a clear answer, but you would like to have some alternatives to play with. So, oh, actually, it's already here. I don't have to type. Who is the best classical composer of all time? Okay, think about that. We may have our own favorite answers to it. And let's see what the LLM generates. And there it is. This is Beethoven, Bach, Mozart. Those actually usually come up when I do that. It's not always the same, but they are all often there. And you see that the confidences here, they are the semantic densities around those answers. They're kind of in the mid-range, 0.6 or so. And if you look at the semantic space, this is, of course, a lower dimensional visualization of the large dimensional semantic space. And you see that some of these answers are more confident, others are a little bit outside. And this way you could get multiple answers and get some confidence of what the right answers are. And in this case, you can see there's really no right answer. They are just confident to a certain degree. But we can ask something else where there is actually a correct answer. What is the prime factorization of, it's here too. All right, 4095. You can do this in your head, right? Well, at least with a calculator, maybe, but it's not as easy. I'm actually still quite impressed that LLMs can do something like this. And they get it right. You know, they get it right just about every time. And you can see that the confidence is clearly higher. I mean, it's at the 0.8, 0.7 level. And you put a threshold of what kind of uncertainty you can tolerate. But here it's actually quite high. And we can say almost all of them are near the center. So we can trust this answer pretty well. But we can make it harder. What is the prime? Oh, yeah, here it is. This is much harder to do in your head. And it is actually too hard for this particular model as well. And it confidently, gives you all kinds of answers, telling you, yeah, the prime factorization is this. And as far as I checked, none of them are correct. They're all wrong. And you have no idea of knowing because LLM gives you that just as well as the previous one. But look at the semantic density, 0.4, 0.3, 0.2. And we can actually tell that in this case, the LLM doesn't know what it's talking about. So we have actually a way of deciding how trustworthy the answer is and making decisions based on that. If it's part of a large multi-agent system, it might still be useful as a guess, but we give it the weight that it deserves. So I wouldn't trust anything at 0.2, but if it's 0.8, I might actually take it as more likely to be correct answer. So that's a mechanism, a numerical mechanism that is kind of a nice metric. If you like to play with it, here's again, a simple URL that helps you to get to the blog post, which then has links to the paper and the code and the demo itself. Okay. All right, so that was the first topic, trustworthiness. And of course, we're still working on it, and there's also interesting extensions. And what do those LLMs do in a network? When they talk to each other, we can also pass along this trustworthiness information. And they can be wary if it's like you are talking to somebody and you sometimes kind of can tell that they are lying, right? You know, that's kind of what we're getting at here. So it's saying that this is the prime factorization, and on the forehead is 0.2. And it's like, no, I'm not taking that. And then you maybe prompt it differently, ask another expert or so. So these multi-agent networks can become much more powerful if they have that kind of a metric. All right, so now fine-tuning. So like I said, it's not just that you're retrieving the information, or it's not also that you may have had this information in your pre-training, so you know it. But fine-tuning is becoming a cottage industry of its own. Again, you need perhaps open source models to do that. But you could fine-tune models to be better at math, for instance, and that actually, or coding. At least those have been done for quite a while, but you could imagine other kinds of experts, medical experts, for instance, medical decision-making, or just political negotiations, taking other people's perspectives into account, being convincing, things like that. So fine-tuning is adding a behavior on an existing general behavior so that it becomes better. And you do have to have some kind of a training set, a data set to do it. So that's, like I said, something that's been happening, but now there are new ways of doing it. All right, so currently, most of fine-tuning is done with reinforcement learning with human feedback. It's not for, it's with human feedback. And there are standard reinforcement learning methods like PPO and GRPO. And what they do is they try to estimate the gradient, like which way should they change their action selection so that their rewards get higher in the future in this set of test examples. So it's action space exploration. You try to go greedily towards where the action give you higher reward. And that's on the left. So you have a model, and then you have another model that's fine-tuned. And then there's another approach where you train another system on the side of the LLM to be the fine-tuning adaptation or modulation. So it's called adapter, and 𝗲𝗲 is one of those mechanisms. So then you are summing up the pre-trained model and the adapter in order to have the specialist. So that's, those are some of the current approaches. So one thing we came up with was dust off this mechanism that's been around since the 70s called evolutionary strategy. And that means that you are doing search in the weight space. Here's a little animation that shows you how that works. The red dot is always the best one that you currently have. The blue dots are your current population. So you have a population-based search. You're not just changing one solution to be better, but you have a whole bunch of them, 30 or 100,000 of them, and they are searching around the current best solution. And then, let me see if I can play it again. Yeah. And then when you find a good solution that's better than anything that you have currently, then you move the whole population around it. So it's kind of like exploratory search. And this has been, there's a really powerful mechanism like that called CMAES, which is trying to estimate how things really change, like structure of the search space. And this was used even by OpenAI, just very recent, well, not very recently, in 2017, to demonstrate that this can be a powerful reinforcement learning mechanism and parallelizable. So the question is, can it actually scale to LLMs? I mean, nobody's ever really tried. I mean, modifying the weights of an LLM. We have billions of weights, billions of parameters, billions of knobs to turn at once in order to make progress. It seems like it's a daunting task for something like evolutionary strategy. But it turns out it actually works. Here's again the same kind of visualization on top. And in the bottom, there's an example of trying to solve a problem with the current solution. I mean, the visualization is 2D, but the search space is up to 8 billion dimensional. We can't quite visualize that directly, so you have to do it in a lower D. But the task is the countdown task. It's a kind of a math puzzle. You're given a bunch of numbers, 28, 3, 4, 52, for instance, and then you have to form a formula with plus minus multiplication and division so that it equals 44. And there's one solution right there. that gives you 44. And this is something that LLMs can do if you fine-tune them to do it. They become experts on this countdown task. And that's what's happening here. As the dot moves, the orange dot moves, you get new models that have their weights changed, and they are better at this countdown task. And in the bottom here, you see what they are currently doing, what they're currently thinking. So let's see if I can run it. OK. Yeah, now it started. So it's a screen capture. There's the same kind of evolutionary strategy mechanism. And as it moves, you can see some of the responses in the bottom, and they become more complicated. You can see them do some search, and eventually, right around now, they actually get it right. They become really good at this countdown task. And here's some data on it. Again, open source models. This guy, in this case, they were 𝗀 and llama. And compared to the reinforcement learning techniques like PPO and GRPO, it's actually quite a bit better. And this was a big surprise for us, or anybody, that this kind of search can be done at the parameter level when it's being done with RL in the action space so far. And it also works with small models, like the top one is 500 million, and reinforcement learning can't do anything there, but we can increase the performance quite a bit. So it's interesting what's happening. We're still trying to understand what exactly is evolution finding in these cases. Let's see. This next slide. There you go. So this gives us a little bit of a hint. This is another task. You are answering questions. And by and large, LLMs are really verbose. They like to be chatty. And we are fine-tuning them to be concise. Just give me the answer. I don't need a story. Just give me the answer. And here are two curves. The top one is the evolutionary strategy. The bottom one is, I think it's GRPO, reinforcement learning. And there are two dimensions. How much is changed is on the x. And it turns out that reinforcement learning only gets this task to work if, meaning it only comes up with concise answers, if it changes the models a lot. And evolutionary strategy doesn't change much at all, but it gets a very high reward, very concise answers. So something is very different. What was really amazing was that evolutionary strategy, in this case, worked with 2 examples. It just needed to see 2 concise answers, and the evolutionary strategy was able to figure out how to change the billions of weights so that all the answers became much shorter. So there's something fundamentally different and new, and this is brand new. I mean, the paper came out a couple of weeks ago. So we're still trying to figure out how general this is, this principle, and especially what makes it work. Because we think that we tapped into something fundamental in how knowledge is represented in LLMs. These changes that evolutionary strategy makes are somehow systematic. And if we can understand that, we might come up with better LLMs in general. And I think this is a great example of new ideas. We should try some new ideas. We shouldn't just everybody be doing the same thing. AI is a lot like 5-year-olds playing soccer. The ball goes over there, everybody goes there. Ball goes over there, everybody goes there. But there's a lot more diversity that we can have in these ideas and find something like this, and it might lead to progress. And that maybe is more the role of the academic research community, because they can explore, but industry may have to have practical constraints. But that's why there's both sides are useful. OK. So and this is also open source. So you could take it and implement it and try it on your own task and see if the evolutionary strategy works for that task. All right. Next, last topic. OK. So complex tasks. It turns out that reasoning is actually not just puzzle solving, but when people build skyscrapers, they manage a hospital, put together an iPhone. iPhone requires 1 billion people. There are 1 billion people who have some role in putting together the iPhone. And if we want to have that kind of reasoning tasks, we have to have LLMs that actually keep track of those reasoning tasks. And this was a bad news that came out a few months ago from Apple Research Group. These LLMs can't handle long-running tasks. Even 𝗬𝗲𝗻𝗀𝗀𝗀𝗀, which is where you move these disks from one peg to another and eventually want to have all of them on the other side. You can't put a larger one on top of a smaller one. They can do about 4, maybe 5, but then the entire reasoning chain just collapses. And they get nothing. I mean, they make mistakes and fail. And now, let's see. The idea is that we could maybe approach this with multi-agent systems. So here's actually a visualization of a single agent, the big agent, the big LLM, trying to solve this. OK. I have to move over here to show it. So here, this is how 𝗲𝗲 of 𝗲𝗈 works. But the big agent with 8 disks makes a mistake. And that is a big disk on a small one, and it doesn't work. It's an error, and a trial fails. But what if we use multiple agents? Massively decomposed multiple agents. That means that we make as small tasks as possible assigned to those 2 agents. And also, we let the agents vote. Like if you have an agent that's trying to make a move, they may be incorrect. But if you ask several of them, you usually get the right answer by voting. And those both are needed in order to make this work. So there's 1 agent per move. And there's 1,000 agents here, and as they turn from blue to green, they make their move. And you see that this actually solves the 8-disk task. So those 2 ideas, maximal decomposition, making the individual task as simple as possible, and then having multiple LLMs vote to get rid of errors, works. And this is where the punchline is. So actually, we have a scaling law that shows that we only need about 3 or 5 votes, and we can have no errors in these tasks that run for very long. And then we can have reliable solutions even with 20 disks. So that's the punchline. Million agents, same devisualization. The blue turns into green, and there's million agents on this display. And they are moving these 20 disks, and eventually all the disks end up where they need to be, like right there. And this is actually a visualization in an immersive room, and it's pretty impressive, and it's all over it. But this shows the million agents. It's just a little hard to have the resolution high enough to show million dots. But that's what's happening here. So a million agents is all you need if you want to solve these very big problems. OK, so to conclude, agentic AI is turning into multi-agentic AI. And we need some new technology to make it work, including reliability estimation, fine-tuning, and taking advantage of these massively multi-agent systems. But once we do, I believe that this is something that can be taken into the real world, and we can safely deploy these systems and have them work alongside us and solve really hard problems as well. So that's it. That's my talk. Thank you. OK, I think there's a mic somewhere if there are questions, and we should have plenty of time for questions. If there. Yeah, there's a mic in the middle if you want to walk over there. And I think people are missing the mic, going for the exit.
Have you seen any of these techniques applied in industry?
Well, yeah, I mean, that's what we are also trying to do. But our lab does basic research, fundamental research, and then we have, that's my group, and then we have another part of the AI lab that builds these platforms. So 𝗦𝗲𝗀 is a platform that is something that can be taken to industry, and we have several, maybe 20 or 30 now applications that have been built, partly by us, but we also want to make it open source so that anybody can do it and use it. So absolutely, and it's ready for that, yeah, happening now, yeah.
LLMs are usually trained to, are they rewarded for guessing as opposed to saying, I don't know? There's been some work about training LLMs that say, I don't know. Have you done any work with that?
Yeah, that's a very good idea. That's Anthropic and others have done that. You could fine-tune them to do that. But the problem is still fundamental, more fundamental, that the LLMs do not know what they know. So it's very hard for them to even answer, I don't know, because they don't really have access. They don't have introspection. This is actually my pet research direction. I would like to build agents like that have a sense of their own thoughts. Like, you have a very good idea what you know. So, like, trying to remember a name of a person. and you know that name, and it starts with an S, but you can't get to it. And maybe a few minutes later it pops up and you know it. So humans are really good. They have some mechanism of organizing knowledge so that you know that it's there even if you don't catch it. I mean, we don't necessarily want it to be LLMs have tip of the tongue phenomenon, but they should have this ability to recognize whether they've seen something. And the I don't know is very complex because it may mean that have you actually seen this fact or do you know the answer to that? But it could also be that it's more general, like this is a very difficult question. Who is the best composer of all the time? There's no clear answer. There are multiple solutions, and the LLM has seen many different arguments, so it should be able to answer that too, that I have knowledge about this topic, and there are many possible answers, and make that so that I don't know has different flavors. But all of that bottoms out to having access to its own knowledge, having introspection, having metacognition. And we are not there yet. Whether the transformer architectures can do it is an open question. I think that we probably need to look at ideas from neuroscience, look at human brain and what happens in the tip of the tongue and where the representations might be, and then try to maybe put those into computational structure in order to get there. Yeah, but that's a really important point. Yeah?
Do you think this wisdom of crowds requires differentiation of prompt, or could you use the same prompt with wider temperature?
For the sampling in the semantic density?
Right.
Yeah, that's how it's done. It's the same prompt and then sampling. We only need about 4 samples to get a pretty good estimate, but you could increase that. And it depends on the type of model and the type of question. So one thing, we should develop a mechanism to evaluate whether we've had sufficient samples to get a good estimates of these answers. So that's still ongoing work. But there are other people who are working along the same lines. That I mentioned semantic entropy. Semantic entropy is trying to estimate how likely the answer is going to be correct for this prompt. So is this a good question to ask of this LLM? And that's a little different question. Here we're looking at, okay, the LLM answered this way. How reliable is this particular answer? And both of those are very useful questions to ask. And semantic entropy has to be defined for that particular LLM. It may be different for a different LLM. But these metrics, I think, are really useful, and all of those factors matter. Yeah?
Wondering if you could give us an idea of the amount of compute necessary for the evolutionary strategy system and the billions of parameters, things like that.
Yeah, yes. And it is indeed a lot of computation when you do evolution because you have to have a population. We used 30, and we're now I think using hundreds or something, and each one of them is an LLM, and you have to evaluate it, and then you do it again with another one, and then you have 100 generations. So you can imagine that that is quite a bit of compute. It has so far been pretty efficient, so we don't need to have large validation or evaluation data sets. Like I said, 2 examples was enough for conciseness. It's a little different. We're doing now math reasoning, and it does seem to need more examples there. So yes, it is indeed computationally rather expensive, but it's not outrageously so compared to RL, for instance. So at least initially it looked like it would be much cheaper, and now I think it might be about the same as RL, but that's still to be determined. Yeah.
I'm merely a simple sales guy from New Zealand, so please excuse my LLM naivety. Recently, I saw that Anthropic had released some updates, possibly papers on their website. They had come up with, recently the term MCP, right, as a connective piece to integrate all these different APIs into an agent, leverage or Google Drive and things like that into the more consumer Claude interface. Their recent paper spoke about MCP being a big cause to a lot of, context rot that goes into it being able to think properly because you have all of this different information coming through all these different connectors. Their paper was specific in saying that the better outcome was to teach the agents to write the code to then make an immediate connection as opposed to having the connection be the context in the beginning, therefore solving the context problem and the context rot. Do you think that a multi-agent paradigm is also another way of solving this challenge?
Yeah, that's interesting. I'm not familiar with that paper. I thought you were going to ask about a different one, the introspection paper. But yeah, so that will come up when we scale up these systems. When you have multi-agent system, like here, you can have multiple levels of agents. And the first one gives you the context, and the second one gives another context. And you may run out or define it incorrectly. So that has to be solved. That's what the protocol, in our case, AAOSA, is for. We actually use MCP there. So that's the lowest level of interaction. But then on top of that, we have AAOSA that worries about precisely questions like that. What is the right amount of context? What is the right context I have to give to my sub-agent so that it does the job I'm assigning to it? So it requires a little bit of intelligence to do. And indeed, so far, we started with something that already existed, AOSA. And now we're learning that, hey, here are actually some things that we have to do differently. So for example, what happens a lot of times that these agents think that, hey, I know everything. I don't have to ask sub-agents. And then they give you an answer, and it's totally garbage, because it's just shooting off the hip. And we have to like really, this is where we need these uncertainty metrics and say, I don't think you got it right. You are just not confident. You actually have to go and ask your sub-agents to provide answers. So think about how you can intelligently split it into smaller chunks so you can take advantage of the network. So this is a really good question. We still have to work on it, like how to do this right. But as these networks grow, these networks of agents grow, the specialization, it's not just the specialization that has to be right, it's really also the information that gets passed around that has to be optimized. Yeah. Okay. One more question? Yeah.
Hi, I'm trying to summarize what I've heard so far, and to me it seems like this multi-agent system, maybe you have like, well, how does this translate to my business? And let's say HR would be represented by like, hey, 5 agents, but vote on this is what we're confident to for our output, and then to the next. And then you have this in kind of different functions that work together. Mm-hmm. Is that a good summary of what I've heard?
Yeah, I mean, it is a good summary. Sometimes it might be who has the right relevant knowledge. Like, I think in HR, you would have to look at policies, and they are prescribed. So the negotiation is, am I going to extend the policy, or do you have something more specific, and we should go with that? In other cases, it might be like, where do we do, I don't know, investments now? And you might have different perspectives, and then it's a negotiation of which one is most likely to be successful. So the interactions can be multifaceted in that way, and it depends on the problem, whether it's information retrieval or negotiation or just discovery. They can be prompted either way.
Yeah, thanks. Iron blanket is...
Okay.
Yeah.
Good. One more.
Have you experimented with semantic density across multiple models that perhaps were trained on different corpuses?
Well, yeah, I mean, we had multiple different pre-trained models. I don't think we've ever done it yet with fine-tuning per se, but they do behave differently. I mean, sometimes llama might be more reliable than 𝗀 in a certain kind of question. So we do see these differences. And I think if they open source, we might even be able to understand how they came about, like what they were trained on. But that's a pretty hard task to do. We know so far that there are differences, and we might actually want to characterize them with some certain kind of syllabus, perhaps, before really deploying it and understanding how reliable these metrics are. But in general, if you look at semantic density, it's really agnostic to all that, because it's really just the density of answers. Whatever the model, whatever the topic, you will have some density. And it's a relative density that matters then. So I think it would work pretty much across. Okay, I got 6 seconds. Anybody? All right, good. Thank you.